Thanks. So first of all, let me thank the organizers for the invitation and for the organization of this nice workshop. In my talk, I will discuss coherent elastic neutrino-nucleus scattering in the standard model and beyond. So this is the outline of the talk. I will start with a brief introduction about this coherent elastic neutrino-nucleus scattering process, also called CEvNS. In particular, I will discuss the recent observation of this process at the Coherent experiment, and also the recent claim of an evidence of CEvNS at the Dresden 2 reactor experiment. Then I will comment about some of the physics potential of this process, both in the standard model and beyond. And in the second part of the talk, instead, I will discuss CEvNS as a background for dark matter searches. In particular, I will discuss the impact of these recent CEvNS observations on the so-called neutrino. So the coherent elastic neutrino-nucleus scattering is a neutral current process in which a neutrino scatters off a nucleus, which acts as a whole, as a single particle. So in the standard model, it occurs via the exchange of a Z boson. And this process arises when the incoming neutrino energy is such that the nucleon amplitudes sum up coherently. So this means that the momentum transfer in the process is smaller than the inverse of the nuclear radius. So there is an upper limit on the incoming neutrino energy, which is of around 100 MeV, depending on the target material. And this leads to a cross-section enhancement. Indeed, eventually, the CEvNS cross-section turns out to scale with a number of neutrons squared. And this cross-section can be quite sizable, in particular, few orders of magnitude larger, for instance, than the inverse beta decay process, which was first used to observe neutrinos. This process was first theoretically predicted in the 70s. However, it had eluded detection during more than 40 years because it's actually an exceptionally challenging process to observe. Indeed, despite the magnitude of the cross-section, it was not observed for so long because it gives rise to very tiny nuclear recoil energies, which are very difficult to detect. So this plot shows the typical magnitude of the CEvNS cross-section in blue compared to other neutrino cross-sections. For instance, in red, there is inverse beta decay. And this other plot on the right instead gives the dependence of the cross-section in terms of the neutron number. And also it shows here the measurements of this cross-section by the Coherent experiment, first with the cesium iodine target and then with liquid argon. Also, it shows some upper limits on the cross-section, which have been set using solar neutrinos and reactor neutrinos. Okay, so this map shows the current status of CEvNS experiments worldwide, and there is indeed a global effort from the experimental community trying to measure these experiments. So the first observation has been made, as I was saying, by this experiment Coherent in the US, which uses as a neutrino source stopped pion beams. I will tell more about this in the next slide. I will also discuss about this Dresden 2 experiment, which is also in the US and uses instead reactor neutrinos. And then, as you can see, most of the other experiments actually uses also reactor neutrinos. Indeed. So what about the neutrino sources that we can use to try to measure this process? So these sources should have some preferable requisites that are the production of a high flux of neutrinos, a well understood spectrum, possibly the production of multiple neutrino flavors, the possibility of locating the detector close to the source, and also the possibility of knowing the backgrounds quite well in order to reject most of it. So the Coherent experiment uses neutrinos from pi dars, and in particular, the source is the spallation neutron source, in which a flux of a beam of protons hits a mercury target, and pions are produced. The negatively charged ones are captured right away from the nuclei, whereas the positively charged ones decay at rest, that's why pi dars, and they produces a prompt flux of muon neutrinos and delayed fluxes of electron neutrinos and muon antineutrinos. So these are the typical fluxes from pi-dar source of neutrinos. But as I was saying, most of the other CEvNS experiments instead uses neutrino from nuclear reactors. So this is instead the typical flux from a reactor source. In that case, there is an advantage that sorry.
The flavor of the neutrino is very important.
Sorry?
Is the flavor of the neutrino important?
No, in the sense that indeed it's a neutral current process, so actually it's sensitive to the total flux. But well, it depends on the model that you want to study. So maybe it's interesting to have different flavors.
And it was never measured with
So for instance, neutrinos from nuclear reactors, in this case, the flux is one single flavor because only electron antineutrinos are produced. But yeah, the fluxes are in principle much larger, but also backgrounds are more important. And the recoil energies that are produced are also much smaller. So it's more complicated to observe CEvNS with these experiments. Also, some other sources have been discussed. For instance, these chromium-51, geoneutrinos, or also the next generation neutrino beams could also be used to probe CEvNS. So concerning the detection strategies, well, we need to observe low energy nuclear recoil. So you will understand right away that basically these experiments share the same detector technologies like direct detection of WIMPs of their matter. And so basically three techniques can be used. So the observation of phonons, of ionization, or photons via scintillation light. So for instance, Coherent uses scintillation as a detection technique. Okay, so this table summarizes some of the experiments that were shown before in the map. And as I was saying, Coherent, which is the first one that observed the experiment, the process, which uses pi-dars as a source, whereas most of the other ones are reactor basis, as I was saying. Yes. Okay, so the first observation of CEvNS was made by Coherent in 2017 using a target of cesium iodine, actually only 14 kilograms of target. So it's one of the smallest neutrino experiments. And this is possible because, as I was saying, the cross-section gets this large enhancement. So even a small detection target is enough to, in principle, to observe this process. And more recently, last year in 2021, they have released an extended data set using the same target and also have improved the statistical analysis. Meanwhile, they also observed the process using another detector made of liquid argon in 2020. So currently there are no observations using reactor neutrinos, but this year there was this claim by this experiment of a possible evidence of CEvNS. This experiment uses neutrinos from the Dresden 2 boiling water reactor in France. So a huge flux of neutrinos is produced here, and they use a detector of a germanium detector. So in this paper from February, they claim this suggestive evidence of CEvNS, which is reported with a strong preference with respect to the background-only hypothesis, but this result is very strongly dependent on the quenching factor model. So in this kind of experiments, which are based on ionization, the quenching factor is actually a relevant parameter. So the quenching factor describes the observed reduction in ionization yield produced by a nuclear recoil when compared to an electron recoil of the same energy. So this quantity is very relevant in these experiments, and it is often not well known at low recoil energies. So you understand it's a major source of uncertainty in this result. So this plot shows the quenching factor and the function of the nuclear recoil energy. The shaded areas are basically the region of parameter space, which has been probed in red by this experiment and in orange by this other CEvNS reactor experiment CONUS. And these colored lines refer to three different quenching factor models. So you see that until here, until the region which is probed, basically the three models could in principle explain the data, but if you if you go to lower energies and you extrapolate them, you see that very large differences are possible. And so this is indeed a major source of uncertainty. So let me go back to the features of this CEvNS process. So the CEvNS perception is well calculable in the standard model, and in full generality, it contains two contributions, a vector one and an axial vector one. However, the axial vector one does not receive this enhancement, this coherent enhancement, and it's also spin dependent. So it's basically small for most nuclei, in particular for the heavy ones, which are the ones that are used in these experiments. So we can safely neglect it. And we can focus instead on the vector contribution. And we can see that the relevant ingredients are, well, the Fermi constant, which is a standard model parameter, the mass of the nuclear target, a kinematic stir, a nuclear form factor, which gives, let's say, the information about the nuclear physics, and it is approximated to 1 in the case of full coherence. And then we have this weak nuclear charge, which is the factor that eventually encodes the typical n-square dependence. And this is, well, it's given by this expression. So you see that there is basically an accidental cancellation. So this term goes to 0 because of the value of the weak mixing angle. And we are left with n squared. So the observation of CEvNS has opened the window to a plethora of possibilities concerning both tests of the standard model and also the possibility of study nuclear physics, for instance, nuclear form factors and nuclear neutron radius, or also to study, well, supernova and astrophysical neutrinos like solar neutrinos. But also, CEvNS, it has been proven to be a powerful probe for VSM physics. For instance, the existence of new interactions in the neutrino sector, non-trivial electromagnetic neutrino properties, and the possible existence of sterile neutrinos, because as I was saying, this is sensitive to the total flux. So we can see if there is a depletion in the oscillation due to the oscillation into a sterile state. And CEvNS is also relevant for dark matter searches, but because in this case it acts as a background. So in this talk, I will focus on some of these physics potential. Let me start with the standard model precision test. So as we have seen, the weak mixing angle is a standard model parameter which enters the CEvNS perception. So we can try to determine the value of this parameter at low energies. That means at low momentum transfer, in particular in a region which is usually not probed by other experiments. Indeed, we have very good measurements of these parameters at higher energies from colliders, but here, let's say around 10, 100 energies, we have no good determinations from the experimental point of view. Of course, we can predict the standard model value from the RGE running, which is shown here as a blue line, but it's interesting also to probe it experimentally because a possible deviation from the expected value would be a clear hint for the existence of new physics. So in these two plots, I took them from these two references, which analyzed the coherent data from 2017 and the liquid argon data, both separately and combined, and they give some best fit values for theta weak. Instead, here I'm showing the running of this parameter as a function of the energy scale, and I'm showing here so these best fit limits and the error bar from this analysis. And also here I'm showing the result from the analysis of these Dresden 2 reactor data, which I've presented before. There are two different values because, as I said before, this result depends on the quenching factor model. So we analyze them assuming two different quenching factors. And you see that especially in one case, the error bar is huge. This other plot, instead, it's the same, it's the running, but it shows some predictions for a future experiment, a scintillation bubble chamber, which would use an argon detector and reactor neutrinos. Still concerning this standard model precision test and the weak mixing angle, instead, I'm presenting here some preliminary results from an analysis that we are almost about to finish. Where we are analyzing the more recent coherent data from last year, 2021, and the liquid argon data set, and we are also combining them. So this plot shows the reduced chi-square profile for these data sets, and it gives this best fit value. And also here I'm showing the running again with the result from this analysis. And you see that it's very compatible with the standard model expectation. But I was saying before that CEvNS can be used also to probe VSM physics. In particular, if we talk about neutrinos, one of the most studied VSM scenarios are the so-called neutrino non-standard interactions, where we assume basically to have a new vector interaction mediated by a heavy vector particle. So these neutrino NSIs can be formulated in terms of this effective for Fermion Lagrangian, which is written here. And these epsilons are the NSI couplings, which quantify the strength of these NSIs in terms of G Fermi, and they can be either flavor preserving or flavor changing. In these plots, I'm showing the results from the coherent analysis that we did for these flavor preserving NSIs, electron ones and muon ones. Here, the yellow and magenta are for the two separate data sets of cesium ion and liquid argon, and instead these plots in blue are a combination of the two. So first of all, we see that the muon ones are more constraining, and this is because the contributions to the seventh rate from muon neutrinos is more relevant at coherence. And in the case of the electron NSIs, we get that if we analyze the two data sets separately, we get only one band. And instead, when we combine the two of them, there is a degeneracy which is lifted, and we are left to two different bands. So this band is basically where the standard model lies, which is 0, 0 here. But we have also another band which is allowed, and it's where basically the NSIs mimic perfectly the standard model contribution, because they contribute as minus the weak charge that we expect in the standard model. So we can also probe the flavor changing NSIs, and this is instead the results that we obtain in terms of flavor changing parameters, epsilon tau, and the flavor preserving ones, EE and mu mu in this case. And well, also here basically we see that the muon ones are more constraining, and when we combine the two data sets, also the results here is more constraining than when analyzing the two data sets separately. Another possibility, so as I was saying, the typical NSI, let's say, assume the presence of a vector interaction, but mediated by a heavy particle, so it can be integrated out. We can also assume instead that we have a new vector interaction, but mediated by a light particle. So in this case, our CEvNS cross-section will be modified in this way. We have let's say, a new contribution which depends on the mass of this mediator. And we can basically express our result in terms of a single parameter if we assume universal couplings, let's say, both to the neutrinos and to the quarks. So our exclusion regions here, these are 90% confidence level contours, and these are 1 to 3 sigma. Are given in terms of this coupling of the new mediator and mass of the new mediator. So again, this result is from the analysis of coherent data for liquid argon, cesium diagram, and the combination of the two, and this is instead from the analysis of this Dresden 2 data. We see that there is some interference which is possible with the standard model, which gives actually a destructive interference. So there is a small region which opens up there. And in general, we see that these reactor data are a bit more constraining, in particular in this region around 1 MeV compared to the coherent one. Similarly, we can also consider a light scalar interaction. In this case, the interference with the standard model is not possible because there is a chirality flip. So we just need to add this extra contribution to the standard model cross-section. Also in this case, we have a dependence on the mass of the mediator. And again, I'm showing here the limits on this new coupling and mass of the scalar mediator. And also in this case, we see that the reactor data actually here are better, are more constraining than the coherent ones, especially at low masses. Another possible DSM scenario that we can study is the so-called sterile neutrino dipole portal, in which we assume the possible transition of an active neutrino to a massive sterile state, which is induced by a magnetic coupling. So the relevant Lagrangian is this one. This lambda is a matrix. And we actually express our differential cross-section in this scenario in terms of an effective parameter. This effective magnetic moment is a parameter which encodes entries of this matrix together with entries of the electronic mixing matrix. Okay, so our results are given in terms of this parameter and the mass of this sterile state which is produced in this interaction. Of course, there is a kinematics limit on the mass of the sterile state, which is dictated basically by the energy of the incoming neutrinos. So for instance, for reactor neutrinos, more or less around 8 MeV, which is the maximum that can be produced. And again, here there are the exclusion regions which are obtained from Coherent and from Dresden too. Again, the reactor data are a bit more constraining. And I'm also showing here for comparison, for instance, a limit that has been obtained with another CEvNS reactor experiment, which is Texono. And okay, well, this paper was from last February, so we still had this preferred region for the xenon quantum excess, which now has disappeared, but just to give an idea of where this reactor, Dresden 2 reactor limits lie. Okay, now I would like to change a little bit the topic in the sense that I will still discuss CEvNS, but now not like a probe, like a signal, but as a background. So, well, we are interested in these direct WIMP searches because if dark matter is made of particles like WIMPs, which interact among themselves and with the standard model particles, then we can try to detect it. And one of the strategies that has been envisaged at this scope is the so-called direct detection, which looks for the energy deposited within a detector by a dark matter nucleus scattering. So we have already seen this plot already in the talks yesterday, which shows the current status of spin-independent with nuclear interactions. We see that there are already many experiments which have probed a large region of this parameter space, have excluded it. And in the near future, these experiments plan to further improve and to explore lower and lower cross-sections by improving the exposure and lowering the backgrounds, and also lower and lower WIMP masses by improving the energy thresholds. So in this kind of plots, we also usually see this orange dashed contour here, which is the so-called neutrino floor, and which is in general seen as a hard and irreducible background for these kind of searches. Indeed, there are some neutrino backgrounds which are relevant for these direct dark matter detection experiments, and these arise from solar neutrinos, from atmospheric neutrinos, and from the so-called diffuse supernova neutrino background, which stems from the cumulative flux of neutrinos emitted in the core collapse supernova explosions along the whole history of the universe. So this plot shows the neutrino fluxes expected from these different astrophysical sources as a function of the neutrino energy. We can try to compute the expected recoil rates from these astrophysical neutrinos using CEvNS, for instance, on nuclei of xenon, of a xenon experiment. And it's
what are the uncertainties on the basis roughly?
So yeah, I will show them. Some of them can be quite sizable, like even 20% or so. Indeed, yeah, of course, it's a major source of uncertainty. I will comment that. So it's interesting to try to superimpose what we expect from the expected recoil rates from WIMPs. So for instance, a 6 GeV mass WIMP would mimic almost perfectly what we expect from boron-8 solar neutrinos, whereas a heavier WIMP of 100 GeV would also mimic the expected rate from atmospheric neutrinos. So these neutrino backgrounds inducing CEvNS in this experiment will produce nuclear recoil spectra, which can have strong degeneracies with those expected from spin-independent wind interactions. So increasing the exposure of these experiments does not imply a linear improvement of the sensitivities, but rather it would lead to a saturation of the discovery limits, which is what typically is referred to as a neutrino floor. However, people have started more recently to talk about neutrino fog or something like this. The idea is that we should not see this as a hard limit. First of all, because it depends, this neutrino floor depends on many uncertainties. For instance, astrophysical uncertainties on the wind sector, also nuclear physics uncertainties, which affect both the neutrino and the wind rates, the neutrino flux uncertainties, which are for sure very relevant, but also the possible existence of new interactions in the neutrino sector, which could change these the rates, the neutrino rates. Moreover, this background, it's it should not should be seen as a hard limit, because in principle it could be overcome with different techniques. For instance, measurements of the WIMP and neutrino recoil spectral tails. They mimic them pretty well, but not always perfectly, especially if you look at the tails. Directionality, measurements with different materials, and so on. Maybe not all these techniques are, let's say, implementable right now, but with some more improvements in the technology could be exploited. Okay, so let me. So here, for instance, there is a table with the typical uncertainties on the fluxes. So concerning your questions. And so let me define here what I mean by WIMP discovery limits. So a discovery limit is defined as the smallest WIMP cross-section for which a given experiment has 90% probability of detecting a WIMP signal at least 3 sigma. Of course, it's a choice, it's a definition. But okay, in general, to compute these discovery limits, we need to define a likelihood, which is in general defined in this way. So we assume that the number of events follow a Poissonian distribution, whereas the uncertainties, which are encoded in this factor, follow a Gaussian distribution. And then the profile likelihood ratio corresponds to a test statistics against the null hypothesis, in which we assume only the 7th background, versus the alternative hypothesis, in which we have the 7th background plus the WIMP signal. So this is the standard way of computing these discovery limits. So these uncertainties on the neutrino flux, for instance, are usually taken into account. But we wanted to go a bit further and try to include other uncertainties which could affect this computation, in particular, for instance, the nuclear physics, and also, for instance, the value of the weak mixing angle. So our likelihood is defined like in this way. We have an extra term which includes some extra uncertainties which can affect the 7th background. So we perform some different analyses. The first one, it's the one that we call data-driven analysis, because we said, okay, if these uncertainties, for instance, on the weak mixing angle or on the nuclear form factor affect the 7th cross-section, we can just extract the value of the 7th cross-section from this coherent data, which has measured that, and together with the error bar, and we can just include it as an uncertainty in the computation of the discovery limits. So this is what we did. We extracted from this coherent data the 7th cross-section central values with the standard deviations, and we weighted the theoretical standard model value of the cross-section by a multiplicative factor, which we extracted from this data. So this plot shows the value of this multiplicative factor for each energy bin of the coherent data set, for the cesium iodine data and for the liquid argon one. So basically, when n sigma is equal to 1, this means that the experimentally measured cross-section is exactly equal to the theoretical expected one. If it is smaller, it means that the experimentally measured one, it's a bit smaller. And this is relevant because now if we have a look at the results of the discovery limits that we computed, taking into account these uncertainties on the 7th cross-section. So the solid lines are the discovery limit that we expect in the standard case, and the dashed ones are the one that we computed, including this uncertainty. This is for a xenon experiment, and this is for argon. In this case, we are applying directly the data from cesium iodine of Coherent, because the nucleates xenon and cesium iodine have very similar properties concerning the atomic mass number and so on. And we also compute these limits for different exposures from 1 to 1000 on the year. So we see that in this case, the discovery limits basically improves. And this is because if we go back here, we see that these values of the experimentally measured cross-section are almost always smaller. So we are basically predicting less background events. And that's why our discovery limits improve. In the argon case, the situation is the opposite, although the effect is also milder. Okay, another thing that we wanted to check was the impact of the uncertainty on the weak mixing angle on these discovery limits. As I said before, CEvNS can be used to determine the value of this standard model parameter at low momentum transfer, but at the moment the coherent data are still affected by a large error bar, so the determination of the weak mixing angle at those energies is still affected by an error of around 10%. So we allowed for a variation of these parameter around the central value with a range of 10%, and we computed the discovery limits with this uncertainty. So we see that the only place where we see some effect is around here, where the solar neutrino fluxes are relevant, and this is because we have huge fluxes in this region, which is about at let's say low wind masses, and the effect is to slightly worsen the expected discovery limits. Another possibility is to try to investigate the impact on the uncertainties on the nuclear form factor. As I said before, also also the nuclear form factor can be extracted and from this coherent data, and also in that case we still have around 10% of uncertainties. For in this case we are varying the neutron radius, because there are differences between proton and neutron distribution, which are in particular relevant for neutron-rich nuclei. And there is still quite an uncertainty on the values of the neutron radius compared to the proton one. So we allowed for a 10% variation around the central value of the neutron radius, and we also computed the discovery limits in this case. And we see that also in this analysis, the effect is mild, and it's visible only in this case where boronate solar neutrinos are relevant. And also in this case, the fact is that the discovery limit is slightly worse compared to the standard case. Actually, this uncertainty affects both the CEvNS background and the WIMP signal, and that's why somehow the two things cancel and the effect is not so sizable. So before I've shown to you that we can use CEvNS to probe some new interactions in the neutrino sector, for instance, new light vector mediators. So we can try to ask ourselves what happens if these interactions are present and how they change these discovery limits. So we computed them introducing this light vector mediator. We fixed the coupling at the maximum allowed value from coherent data. And we see that the impact is huge in this case, especially at masses, at WIMP masses below 10 GeV or so. And the discovery limits are much worsened, because in this case, the new contribution increments a lot the neutrino backgrounds. The situation gets reverted at higher WIMP masses, because what occurs here is that, this contribution depends on the mass of the mediator and the momentum transfer, basically. So when we go to higher momentum transfer, this contribution is not so relevant anymore. And also we should notice that this contribution is positive, whereas the standard model weak charge is negative. So what occurs here is that there is a destructive interference And therefore, that's why actually the discovery limits improve in this case.
Sorry, Valentina.
Yes.
Just to clarify, when you talk about discovery limit, or you are talking about dark matter discovery?
Yes, correct. Yes.
But here you would discover new physics.
Basically.
Yeah.
Yes. Yes. Okay, and the second, well, as before, I mean, another possibility is to consider a light scalar mediator, and similarly, as in the vector case, also here we have a worsening of the discovery limits. The improvement here is not possible because, as before, there is no destructive interference in this case with the standard model. And also, well, in this case, actually, it's true that the effect is large, but a bit milder compared to the vector case. And finally, the last scenario that we considered is the possible presence of a neutrino magnetic moment. As I said before, I mean, this CEvNS data can also probe non-trivial electromagnetic properties. So, for instance, neutrinos could have a neutrino magnetic moment. And in this case, we should add to the standard model contribution this new contribution due to this interaction, again expressed in terms of an effective magnetic moment. And well, the result is again shown here. Also in this case, we see that the contribution is relevant mostly at low wing masses, because this is the region where the corresponding to the low momentum transfer. So this actually gives rise to a spectral distortion, and this is indeed where we expect to mostly see the effect. And again, since we are adding some new contribution to the standard model one, again, as we expected, we get a worsening of the discovery limits. So I come here to my summary. And well, in my talk, I've presented the coherent elastic neutrino-nucleus scattering process. At the beginning, I've discussed its features, in particular the coherency condition, and the fact that it leads to an enhancement of the cross-section, which eventually depends on the number of neutrons squared. So this cross-section is quite sizable. I've discussed that this process can be used to, it has an extended physics potential, and it can be used to probe standard model, to make some standard model tests, to probe the existence of new physics. And I have presented some results which we obtained analyzing recent data from the Coherent and the Dresden 2 experiments. And in the second part of the talk, instead, I have reconsidered the possible variation of the so-called neutrino floor, exploiting these measurements of the CEvNS process, in particular by the Coherent experiment. Well, the take-home message from my talk, I think it should be that, well, this process is quite interesting, and there is a wealth of information expected from forthcoming data. So we can expect that these will have relevant implications for both precision tests of the standard model and to study BSM physics. So thank you very much.
Thank you, Valentina. Yeah. So,
And you have to measure the flavor of the outgoing neutrino in a solvent scattering?
Well,
it means to measure ZFCNC with neutrino. If it's flipper flavor, the neutrino. Is there any hope to do this?
So in these experiments, you don't measure like the.
But if I will put the neutrino detector close to it, is it possible? Or it's the flux is too high, so it's impossible.
I mean, the point is that it's still, I mean, it's a neutral current process. So at the end, you are always sensitive, to this total.
Yeah, but if I know that I start just with electron neutrino,
Okay.
Reactor,
Yes.
and I put a detector for mu neutrino, there is only one, then I can do it in principle, no? And I'm not sensitive to the incoming because I have zero, and I can measure the neutrino, ion, neutrino, electron. To put a bound
On the mixing, you mean?
Not mixing, but yes, something is supposed to be just zero.
Okay, maybe. Yeah, I don't know.
Okay.
yeah. So just a curiosity. So how how bad or how good are assume there is no WIMP in the detectable range of the forthcoming dark matter detection. How well do they perform in measuring this coherent based on the natural fluxes that we have?
Yeah, well, from my point of view, I think, it's actually something interesting and that we should study a bit better, in the sense that indeed, if we do this experiment still, from the pessimistic point of view, if they don't observe anything from the dark matter side, at least they can be exploited to study these neutrino fluxes. And I think actually they already do quite well. If you think of these LZ results and xenon and ton, I think they already put the most stringent limits on, for instance, magnetic moments and so on. So I think that's a way to go, in the sense that at least it's a way to exploit these facilities, and for sure try to, for instance, lower the uncertainties on the solar neutrino fluxes. Yeah, it's so of course it depends on the experiment, on the exposure, and but I think they are good capabilities to study them. They already shown, they have already proven to be powerful in that sense.
Okay, any more questions?
Well, maybe a couple of naive questions. The first one is, let's say you saw a deviation. Let's say you saw a deviation in the running of the weak mixing angle of those energies. What kind of physics could explain it without messing up everything else?
Okay, good question. I don't have an answer right now, but well, I'm pretty sure you could try to cook up some model where you can.
Yeah, the second one was on the neutrino magnetic moment. So if I assume no dark matter, would these new dark matter experiments set the best bound, or is there something else that does it?
Yeah, as I was saying, these LZ, I think the recent results are exclusion limits. They already set I think, more stringent than gamma and Borexino, which up to now were the most stringent ones. I think LZ already does better. That's why I'm saying yes.
Yeah.
These facilities.
Just for precision, I think it would be the best laboratory bound.
Yeah, sure.
If you go to astroparticle probes, the sensitivity is much stronger.
Very good. So I think there are no more questions. So let's thank Valentina again.
Thank you.